Hello guys, very happy good evening to every one of you. And guys, now we are just going to see the thermodynamics. So let us have just a 10 minutes of revision. So after having this 10 minutes of revision, we can just continue our classes. Okay. So since we are just seeing the open system analysis, so in the open system analysis, let us have a 10 minutes of discussion. Okay. So before going into that, I will just switch on my stopwatch. So after turning on my stopwatch, I will just have the entire discussion. Okay. Just one second. ॐ नमो भगवते वासुदेवाय नमः. Stopwatch, my dear stopwatch. Okay. Okay guys, then let us start. So you can see flow work. So what is a flow work? Fluid either enters into the system or leaves the control volume, and force equal to pressure into change of area. Okay. So what is flow work? Flow work is F vector of dx vector. Okay. So dx vector is, you can see, this is change in this one. Okay. Suppose if you want to just expand, means force equal to pressure into dA area. So P into dV. Okay. So then specific flow work, specific with just divided by mass. Okay, that's it. So P of dV joule per kg. Okay, that's it. Or joule per kilojoule Kelvin, that is your wish, you can write in your point of view. Okay. Okay. So you can see inlet, generally you can see inlet is minus PI of, it means specific volume, and suppose you feed out in a rate, means minus m dot I PI of A. So outlet also there. So for turbine the control volume is positive, but for boiler and condenser the work done of control volume is generally 0. Okay, we don't do, it means we don't get a work there. Okay, for next one, pump and compressor, you can see work done of control volume is minus of my, okay, minus, that's it. Okay, it means negative work, which means power consuming device. So specific control volume work equal to W of CV equal to minus inlet of outlets specific volume of dP. Okay, that's it. It means specific volume control volume work. This is for generally for pumps, it has been just given. Okay. Okay, minus into I of out V of dP, specific volume of dP. Okay, next one, data of specific control volume, it means WRDC equal minus m dot integral of V of dP. Okay, so specific volume equal to 1 by of density. Okay, that's it. Okay, so next one, you can see work done of control volume is greater than or greater than of compression of piece of pump. Okay, so for pump work so much less we need to give, but for compression we need to give so much of work. So because liquid pump handles liquid higher density, so lesser specific volume work. Okay, so less work in number. But gases, since it is compression, it means compressor, it is gas, high less density, high specific volume we need, so more work we need to do. Okay, so generally compressor work it will be minimum at isothermal process. Okay, it means whenever process isothermal, the compressors take input, it means minimum. Okay, you can this one, this is, so you can see how much the reduction in the entire volume, it means work it has been done. So flow include, you can see highest energy, potential kinetic energy, internal energy, and flow work. Okay, so flow work equal to force into distance, work into PA into L. Okay, so entirely W will be of PV. Okay, so you can see interreversible steady flow, it's entirely kinetic energy, potential energy entirely 0, means you can see work equal to minus I of 0 V of dP. Okay, so internal energy microscopic energy of closed system, and enthalpy is microscopic energy of open system. Okay, internal energy is microscopic energy of closed system, enthalpy is micro energy of open system. Okay, that's it. So the next thing you can see, it means for a pump you can see inlet of outlet V of dP, it means boiler pressure minus of condenser pressure. So next one, control volume work, you can see isobaric pressure is constant, so entire control volume will be and will be 0. Okay, this one. Okay, so isothermal flow temperature constant, WC ln of PA pure P naught. Okay, same as respect to which one, for the closed system. So next one is adiabatic flow, this one PV gamma equal to C. So work done of control volume equal to gamma of PI of VA minus of P naught of V naught. For open system it is gamma minus P input here. Okay, polytropic PV per N equal to constant, so N PI VA minus of P naught of V1 divided by N minus 1. Okay, simple. So here N is number of moles and this one is polytropic, do not confuse gamma, this one. Okay, so next one you can see conservation of mass and conservation of energy. Okay, conservation of mass, you can see m dot I equal to m dot O plus dm of dt. Okay, so conservation of energy is E of I equal to E, it means E of E dot of out plus dE by dt. Okay, that's it. Okay, simple. So next one you can see the entire equation has been given like that, but instead of going like that you just need this one. Okay, Q dot, it means entirely represented in a specific volume. It means specific means divided by mass. Okay, that's it. So Q dot or time also it does depend. Okay, W dot of CV plus change of potential energy, change of kinetic energy, change of enthalpy plus dE by dt of control volume. Okay. So for closed system, you can see Q dot equal to W dot of CV plus dE by dt of control volume. So next one, steady flow. Thermodynamic property does not change with time at a particular location. Okay. So may vary in space but no variation in time. Okay. dm of dt of control volume equal to 0. dE of dt of control volume equal to 0. So m dot I equal to m dot O. Okay. E of I equal to E of O. Okay. That's it. So steady flow of control open system is this one. Q dot I, W dot CO is anything. Okay. Just a simple thing, no need to confuse. Okay. So potential is equal to m dot G z naught or minus of za. So kinetic energy 1 by 2 m dot c naught square minus of ca square. Okay. Change of enthalpy is m dot h naught minus of h. Okay. Next one, nozzle. Steady flow device increases kinetic energy. Yes, definitely it is adiabatic device. Water of control equal to 0. Yes, and you can see change of kinetic energy plus change of enthalpy equal to 0. Okay, that is simple thing. So next thing you can see 1 by 2 m dot c naught square minus of ca square plus m dot h naught minus of h. Okay, this entire thing. So next one you can see in nozzle inlet enthalpy is so much higher, hi greater than of h naught. Okay, so generally Ta will be so much higher than T naught. Okay, so these are the extra things. 1 by 2 C naught. Okay, so density you can see P naught rho naught, it means I think so in R of T naught. Okay, this one. Okay, so only perfect gases interreversible adiabatic flow, this one we need to use perfect gases T naught P naught, this one entire thing. Okay, next one is since it is steady flow means m dot equal to m dot O. Okay, this entire thing I think so you would have known. So this is just interrelated. Okay, so next thing you can see diffuser. Generally diffuser is steady flow, increases pressure, centrifugal compression. So it means you can see in this thing the pressure increases as well as the enthalpy increases. Okay, I think so you can understand. So diffuser, so pressure increases, enthalpy also leads to increases. So outlet temperature will be so much higher than inlet temperature. Okay, so next one, turbine. So turbine you can see steady flow device, power producing. Okay, W dot of CV plus of change of enthalpy equal to 0. So CV plus of change of enthalpy equal to 0, h naught less than hi. Okay, so for turbine and nozzle are a little bit same. Okay, for turbine you can see it means hi less than of h naught, so T naught less than of Ta. Okay, inlet temperature will be so much higher. Okay, so what kind of control volume work is Cp T in minus of T naught. Okay, so Cp is R per gamma of gamma minus 1. Okay, so control volume of this thing I think so you are known. So put here and calculate the equation. So next one, control volume work equal to done at expense of enthalpy only. Okay, control volume work done at the expense of enthalpy only. Okay, so next one is compressor. So compressor is a steady flow and increases pressure of the fluid. Burden of control volume plus change of enthalpy equal to 0. Okay, and everything. Okay, that's it. So next one you can see throttling device. So throttling device is such a simple thing, so no need to just complicate yourself. So you can see flow restriction device and the inlet pressure will be so much higher than outlet pressure. So here in throttling devices the pressure drop will occur but the enthalpy will be remain constant. Okay, I think so you can understand. Since enthalpy remain constant, it means the temperature, the internal energy, each and everything will be constant. Okay, so you can see larger the throttling device, since it has been considered Q naught, smaller throttling device Q naught equal to 0. Okay, this is you can see isenthalpic process. Okay, Q equal to delta is isenthalpic process. Pressure drop without involving any change of control volume due to irreversible presence of friction. Due to the friction, the pressure drop is occurring. Okay, so here you can see P naught of V naught equal to PA of EA. Okay, basic equation. Okay, so it means charging of insulated evacuated tank. Okay, this one you can think M1 equal to 0, it means M1 equal to U1 equal to 0 and M naught is 0. Okay, so internal energy equal to, it means how much the enthalpy we are given, that is the change in specific internal energy. Okay, final specific internal energy equal to specific enthalpy of fluid. Okay, basic thing. So Cp of T2 equal to Cp of Ta. Okay, T2 equal to this one Cv. Okay, T2 equal to gamma of Ti. Okay, that's it. Okay, so charging of an insulated evacuated tank initially having mass non-zero, so some mass is there. Okay, so for that gamma of Ti divided by 1 plus of P1 by P2, gamma Ti divided by T1 minus of T minus 1. Okay, so you think so you can understand. Okay, so this thing I just explained. So volume flow rate is V dot meter cube per second. Okay, volume flow rate, so do not get confused, volume flow rate. So you can see PV equal to V dot. Okay, so next one, cold air and hot air mix means this is a general formula, and turbine and compressor delta W will come. Okay, so nozzle and diffuser, this will run electric heat also, change of control volume will be 0. Okay, So minus V, P naught minus of PA, this one, okay. Mass flow rate minimum if turbine is completely insulated, okay. Okay, I think so I can answer. So let us start our sections, okay. I think so from 10th question we just finished, I think so. So let us go to the next one. So I'll just explain the basic calculation. So because soon we have to just complete, okay. Dun, dun, dun. So you can see this one, the 11th question. So air enters adiabatic nozzle, okay. Nozzle, okay. Pressure 1, T1, velocity 1, okay. Pressure 2, V2, and inlet area 1, and specific CB. So they are asking the T2, okay. So change of kinetic energy plus of change of enthalpy equal to 0, okay. So for this one, C2 square minus of C1 square divided by 2 plus of which one? Plus of Cp T2 minus of Ta, okay. By this you can calculate, okay. T2 you can just generally easily you can calculate, okay. That's it, okay. So here you can see m dot, okay. What is m dot? So what is mass? We really know. So PV equal to mr of T, okay. So R we know, temperature we know, pressure we know. So volume, so P equal to P rho naught of rho I of R I T I, okay. So by this one I think so we can calculate the density, okay. So since m dot is same, so definitely rho 1 A1 of T1 equal to rho 2 A2 of T2, okay. So by this we can calculate the density of one, okay. So put here density of one, each and everything you can put here. So the next thing is it means here we need to calculate the m dot, okay. How we can just calculate the m dot? Just think, velocity is given, okay, meter per second. Pressure equal to force per area, okay. Question number 11 and 13, it will be definitely simple only, okay. Okay, this is also one of the good question, because as I just before thought, they have just taken ms 1 kg, okay. By taking 1 kg m1, it means 1 kg you can calculate the T2 here, okay. So next one, this one. So by this you can calculate the density 1 A1 of T1 divided by density 2 of A, it means T2 of A2, okay. Density 2 you can do P2 equal to density 2 R of T2, okay. I think so about the point. So since this one is P2 R of T2, so P2 R of T2, okay. T2 to T goes cancel. So generally what will be that? P2 of R. So for R of R, what is an R of air? Okay, 0.287 only. That's it, okay. P1 adachai. So you can see this one, rho 1 A1 of C1 equal to rho 2 A2 of C2, sorry, okay. So here C1 will be, here T2 will be, and here you can see C2, okay. C2 will be here. So this one will be T2, okay. Now calculate it, because we know V1 and T1, just calculate, that's it. So we can just go for the next one. So pump handlings pressure from you can see this one. So what is the work done of control volume equal to V of integral of dp, inlet of outlet. So since they have just given density, so specific volume equal to 1 by of density. Okay, so 30 bar 30 into 10 power 3 minus 1 into 10 power 3 Pascal. Okay, so since it is bar, it is given. Okay, so you can see 10 power 5 10 power 5, so divided by 990 kg per meter cube. So just put and we can just calculate the answer. So Pascal is Newton per meter, so this will go, it means this meter cube will go, so meter cube, meter square will come, so this one kg, so kg let us convert to Newton side. So while you just convert, we will get, it means joule per, or sometimes we make it in second also, or since it is kg, kg will be, and it means kilojoule also we make it. Okay, so 30. Okay, simple question. So you can just go for the next thing, for this one. So temperature, okay, they have just given convergent and divergent. Okay, converging the temperature and the pressure of a large reservoir is, so at inlet 400. Okay, this one, okay, 3 bar. A conversion at the exit area of a wall is meter, so this is the exit area. Is the exit area is given the static pressure of the exit. Okay, okay, the pressure is also given, the characteristic also given. So the density of the exit also, so they are asking the rho 2. So since it is m1 equal to m2, so rho 1 a1 of c1, rho 2 a2 of c2. Since we literally don't know what is the velocity. Okay, okay, they are asking the also the mass flow rate m dot. How we can calculate the, it means which one? Velocity. So density 1 we can calculate, so p1 equal to divided by r1 of t1 equal to rho 1. So this one you just put here and you can calculate. Okay, 403 bar is given, put here and you can calculate. So rho 1 you can calculate, and rho 2 also same. So but what is the main thing is that here we don't know the temperature. Okay, suppose a1 we also don't know. So suppose you can say, let us find this one. So t1 p1 1 minus gamma by gamma equal to t2 p2 1 minus gamma by gamma. So we know, it means rho is how much? Rho 2 is density at exist equal to p2 divided by r of t2. Okay, so t1 p1 we know, p2 also know. So by this calculate the p2 and go and put here and calculate the density. Okay, so what will be the mass flow rate? Since m dot equal to rho 1 a1 of c1, rho 2 a2 of c2. So m dot equal to rho 2 a2 of c2, because exit area is given and density exit also we know, but what will be the c2? So you can see reservoir, so c2 square minus of c1 square divided by 2 plus of cp t2 minus of t1. So since we know t1 and t2, by this you can see this one c2 you can just calculate. So put here, you will get the answer. Okay, that's it. So simple question, I think so you can understand. So you can, by this you can calculate the temperature too and put here, and you can calculate the density. So you can see, okay, this entire thing. Okay, cp t0 t0 minus of ta 1 by 2, this one. Okay, so for this cp alone, they have just taken cp equal to r of gamma by gamma minus 1. That's it. Okay, so you can just go for the next question. So at 10 bar and 400 Kelvin is flowing in the velocity through uniform cross section. Okay, so add uniform cross section. Okay, so they're asking m dot equal to rho 1 a1 of c1. So velocity given, area given, calculate the, it means density, p1 divided by r of t1 equal to rho 1. So what is the it is for air? R is 0.287 kilojoule per kg Kelvin. That's it. Okay, so next question you can just go, it is 70th question. So 17, you can see, in a static state, adiabatic flow of air to horizontal nozzle, the pressure nozzle. Okay, pressure 1 T1, pressure 2 T2 given. Okay, perfect gas. Okay, okay, air consider perfect gas, Cp, density, inlet winding. Okay, they're asking the which one, it means C2. Okay, C2 square minus of C1 square divided by 2 plus of Cp. Okay, Cp given, Cp T2 minus of T1. Okay, equal to 0. So calculate, C1 is 0, so C2 we can calculate. Okay, that's it. 17. Okay, that's it. So you can just go for the next question. A compressor undergoes, okay, the following check: V specific volume, pressure, the specific work required to be supplied for the compressor. So work is done on the system. So they have just mentioned here compressor and compression, so B is the answer. Okay, okay, we can just go for this one. So in a steady state device taking place in a device with single inlet and single outlet, the work done per unit mass is W inlet minus V. Okay, is valid for only both reversible, is valid for any reversible, reversible process. Okay, C is answer. So you can just go for this one. So this is the D is answer. Okay, you can generally just read the question and you will get the answer. Okay, so next one you can see, consider steady flow of a adiabatic passage, air flows. So air flows, adiabatic passage. Okay, oh, there are gas connecting the nozzle as well as the diffuser. Okay, so one case nozzle, another case diffuser. Diffuser will be like this. Okay, so here the temperature will be greater than T2. Okay, here that outlet temperature will be greater. Okay, so since you can see air enters the passage 500 and velocity exits 510, so 500 510. Okay, so it is diffuser. Okay, so Cp T2 minus of T1 equal to change of kinetic energy, just put and calculate the answer, we will get answer. Okay, that's it. Air perfect gas. Okay, put here and calculate the answer, this one. Okay, that's it. So next one, nozzle. Restriction is adiabatic converging nozzle. Okay, P1 T1, V1 is 0. Okay, discharge it, pressure discharge. So after discharge, so P2 is okay, exit A2 is given, and flow rate of air. Okay, flow rate, so they're asking Q dot equal to A1 of V1. Okay, so or Q dot equal to A2 of V2, so calculate the V2. Okay, so you can see P1 P2 T1. So what I just told, which one, the T1 P1 1 minus gamma by gamma equal to T2 1 minus gamma by gamma, so P2. So calculate the T2 here. Okay. So after calculating, do C2 square minus of C1 square divided by 2 plus of Cp T2 minus of T1, okay, equal to 0. Put T2 T1 and calculate this one, so calculate C2, and after calculating put A2 into C2, that's it, okay. So calculate T2 and after that this one, so after that C0 flow rate, okay, it is mass flow, but they haven't just, okay, mass flow rate means I think so you can easily do it, so just you can calculate, that's it, okay. I just thought flow rate means it's Q, okay. So you can see this one. So for reversible adiabatic compression steady flow, the water transfer per unit is B, okay, divided by adiabatic compression, the S is given, okay. So for first law takes place this one, so applicable to change of work equal to change of enthalpy. Definitely in my case of scenario, I think so it is B is the answer, okay. Yes, B is the answer. So we can just start this one, okay. So now we'll be seeing the next thing, okay. So this question has been asked in GATE 2001. Oh. So you can see in air conditioning, okay. I'll just read the question, okay. So this kind of question please do in the end of the video, okay. It means end of the your GATE exam. So you can see an air conditioner provides a continuous flow using intake and exit as shown to maintain quality of intake air. Indoor air, the intake supplies fresh air at the cold stream and the two are mixed in the chamber. So cold air, okay, cold air is 5 degrees and okay temperature. Volume flow rate, okay. So do with the volume flow, okay. So the mass of rate of fresh air is 1.6 times. So mass of fresh air equal to 1.6 times mass of cold air, okay. So mass of fresh air divided by mass of cold air equal to 1.6, okay. So air leaves the room through the exit duct 24 degrees Celsius, okay. So rate of heat gained by the air from the room. So they are literally asking the Q dot, okay. So suppose so I'll just write for the cold air. So T1 5 degrees Celsius, P1 105 kilopascal. So fresh air, it means fresh air. Temperature is T2 is 34 degrees Celsius. Pressure is 105. So pressure is okay. Pressure is same, okay. So m dot fresh air will be m dot of cold air equal to 1.6. So we need to find the temperature of the room, okay. Temperature of the room is how much? So temperature of exit is what? 24 degrees Celsius, okay. So by this you can just calculate this one, okay. So you can see Q dot change of kinetic energy plus change of potential energy plus work of control volume plus of change of enthalpy, okay. Change of internal energy. So kinetic energy will be 0, okay. Potential will be 0, control volume will be 0. So Q dot equal to change of internal energy, okay. Which of P1 or V1? So since it is so, maybe Q dot equal to change of enthalpy, okay. So Cp T2 minus of T1, okay. Q dot. So T1 T2 we know, but what is T1? So for the T1 we need to just calculate, okay. So So basic thing, okay, m dot, this one is cold air, cold air of Cp of cold air of so since temperature will be increased, so T2 minus of T1 will be 5 degrees Celsius, okay, convert to Kelvin. So plus of m dot of fresh air of Cp of T, definitely it will decrease, so it's 34, so 34 degrees Celsius minus of T2, okay, equal to 0. So entire equation divided by m dot f, means entire equation divided by m dot of Cp, m dot of Ca and m dot of Ca. So this is cancelled. So Cp T2 minus of 5 degrees Celsius plus of m dot of this one Fp divided by m dot of C, Cp of this, okay. T2 34 degrees Celsius minus of T2 equal to 0. By this, I think so, by this we can calculate the T2, temperature of 2, okay. So here the temperature will be this one, here the temperature will be this one, okay. Cp, I think so, we can just put and calculate, that's it, okay. Let us see what will be the answer. So you can see by this one, it means okay, I think so, is one. By this one you can just generally calculate the entire this one, okay. It means equilibrium temperature. So what then calculate? So by this T2 and Cp, but other thing is m dot is needed, okay. It means m dot of total. So yes, I just literally forgot this one. So m dot of total, we can just find. So m dot of total equal to m dot of fresh air plus of m dot of cold air, okay. So we have only the ratio m dot of fresh air divided by m dot of cold air is equal to what, 1.6. so put here 1.6 plus of 1 equal to m dot of total is 2.6 of m dot of cold air, okay. So PV equal to m or T, okay. So since you can see they have just given volume flow rate, okay. So this one m equal to P volume flow divided by R of T equal to m dot 1. So place here and calculate. Wow, that's just an interesting question, okay. Just put here and calculate, okay, that's it. See guys, basic sense only we needed, okay. Common sense as well as the basic sense. So next thing you can see here, two air stream of mass m1 and m2 entering mixing chamber exit after perfect mixing, okay. So the temperature T1, so let us suppose like this, it's been going outside like this, okay. So they're asking the T3, okay, T1, T2, this one is T3, okay. So m dot, okay, so m dot 1, m dot 2, and here it will be m dot 3, okay. T3 after meeting, so neglect, okay. So what they are asking, they are asking the temperature of T3, okay. Since you can see q dot, okay, q dot equal to m dot total Cp, okay, Cp is just normal thing, so T2 minus of T1, okay. Heat loss for assuming the process, identify the correct exit temperature, okay. So T3, so m dot 1 Cp1 T3 minus of T1 plus m dot 2 Cp2 T3 T3 minus of T2 equal to 0. So T3 we can just calculate, means T3 minus of T1 equal to m dot 2 T3 minus of T2. So m dot 1 m dot 2 equal to T3 minus of T2 will be T3 T1. So in just take T2 outside, just take T we are doing some mistakes, but a small mistake only. See, as I just told, it's a simple thing only, okay? So you can see m dot, this one 1 plus m dot 2 of Cp of T3 minus of m dot 1 of Cp of T1, this one, okay? Just put here and calculate, that's it. As I just thought, literally it will definitely be okay. You can see this one, a gas is heated in a duct as a flow over, consider, okay, electric 101 electric heater system. The gas enters the heating section, the gas enters the heating sections, gas enters, okay, P1 T1 given, so volume fluid V1 also given. So from the gas the heat is lost, okay, Q dot is 51 kilowatts, okay, so this one is W1. So the exit is this one, so they are asking the T2. So Q dot m dot Cv plus of change of enthalpy, okay. So Q dot is given, work done of control is given, so this one is Cp T2 minus of T1, okay. Q dot is work done on the system, so you can see minus 51 kilowatts to minus 101 kilowatt plus of Cp of T2 minus T1, okay. What is m dot? So PV equal to m or T, okay. So PV dot equal to R of T1 m dot, okay. It means for this you need to put m dot here, okay. After putting here, calculate and we will get the T2, okay. That's it. Okay, simple thing only. So you can just go for that fourth question. So this one, a hot gas has to be an ideal gas. Gas turbine, okay, turbine. So P1, T1, P2 given. Subsequently, it expands with also. So it's a compressor, okay. So turbine is this one. And a nozzle. So P1, T1, here P2 also given and expands, so P3 given, it's 1 bar. If inlet velocity is C1 equal, it means if inlet velocity of air to the nozzle, okay, this one C, it means this one equal to 0, okay. So the inlet, okay, the final velocity they are asking, this one C2 is so much, okay. So first we need to calculate the temperature based upon this one, okay. So P1, it means T1, P1 1 by gamma equal to T2 P2 1 by comma, by this you can calculate the T2. So okay, so here the temperature will be T2. So here how we can same again, P it means T2 P2 1 by comma equal to T3 P3 1 by gamma minus gamma. So calculate here T3. Okay, after calculating, since it is nozzle, C2 square minus of C1 square divided by 2 plus of Cp T3 minus of T2 equal to 0. This one 0, calculate C2, that's it. Okay, so you can see calculate the T2, and after calculating the T2 it means this one. Okay, so T3, calculate the T3 same and calculate the T3 and go and apply here and you will get the answer. Okay, that's it. Okay, so let us finish with this question. So calorific perfect gas. Okay, gas turbine with same enters and okay, enters and leaves the gas turbine with same velocity. So they are asking the m dot. M dot is how much? So rho 1 A1 of T C1. So you can see a calorific perfect gas constant pressure. Oh, this one. Okay, enters and leaves a gas turbine. So C1 equal to C2, T1 T2. Power produced W dot CV equal to 4.6 megawatt. So heat escapes Q dot equal to 300 kilojoule per second. So minus 300 kilojoule into 10 power 3 joule per second is what? Okay, equal to work is produced. Okay, so plus 4.6 into 10 power 3 wait 10 power 6 watt plus Cp T2 minus of T1. Here divided m dot. Okay, so minus 300, heat is lost, 10 power 3 minus of 4.6 into 10 power minus 6 divided by Cp T2 minus of T1 equal to m dot. Okay, okay guys, then that's it for this video, and let me see you in the next video. Until then guys, take care, have a good day, bye bye.